Okay, so V is R prime of t. And I'm just going to do it in 2 dimensions because we'll be able to write it down more quickly. Which is dx dt I plus dy dt j. Instead of x prime I plus y prime j, I'm writing it dx dt I plus dy dt j, right? And before we wrote it as x prime I plus y prime j. And then a z prime k if we want that. Okay? Makes no difference. And might as well write plus dz dt k. Okay? In a short time interval delta t, you're changing, actually I could say changing the R vector, okay, is approximately equal to R prime of t star delta t, where t star in the delta t interval, right? Because in a short interval, assuming this is a continuously differentiable function, if the interval is short enough, there's not going to be a hill of beans change between the velocity at one time in that interval and the velocity at another, right? Velocity is changing continuously, so if you make the interval short enough, the variation in velocity becomes insignificant. So we can say this, and this is approximately equal because it does make a little bit of difference where you are in the interval when you evaluate R prime, right? And we only want to use one value of R prime because we can only multiply one value by delta t. Okay? And delta S is your distance along the path, and I've stated it that way previously, so that should be familiar, that idea. If not, make it familiar. Well, the point is moving along the path. So the distance you move is just the magnitude of delta R, right? Delta R is a vector. Okay, now, if you have a path, let's say here's your path, okay? And you have a bunch of short time intervals. Let's say you have time intervals that take you from one point to the next. Okay? Well, you're going to get a bunch of vector delta R's, right? So these could be your delta R sub I, where I goes from 1 to n and all that stuff, right? And the delta R sub i's add up to the vector from your first point to your last that I'll call S, right? But the distance you move along the curve is not the length of S, is it? Now it's pretty close to the sum of the lengths of all these vectors, right? Okay? So the distance along the curve is the sum of the delta S sub i's, where delta S is the length of each of these little vectors, right? And that would be the sum of the magnitudes of your delta R. That make sense? Intuitively? And most of the notation is there. I mean, there's a little more notation you want if you want to prove this rigorously. Right now, we're being a little more intuitive, and we're just building the idea and laying the framework for being able to write this out with complete rigor. Okay? But we're very close. You just have to, well, there are things you have to do. Okay? So the idea is simply that your S vector from here to here has a length, sure, but you're not following the straight line. The shortest distance, of course, is a straight line, so distance along this path is going to differ from the length of this. It's going to differ from the distance directly from this point to this point. So you get an arc distance. Now you've done arc distances of functions of one variable. Okay? Remember, you integrate the square root of 1 plus f prime of x squared dx between a and b, and you get the arc distance between a and b. And that's just because of, you know, a simple diagram in terms of a triangle. Okay? You know, if you've got a delta x down here, and your slope is f prime, then this side is f prime delta x. So this is the square root of, give myself room, delta x squared plus f prime delta x squared, which is square root of 1 plus f prime squared multiplied by delta x, right? Just put this in context. You know, that's how you derive this. It's not a formula that engineers use. It's something any mathematician and any good engineer understands without having to memorize a formula, right? Now, if you use a formula and have to memorize it, you can still be a decent engineer, right? You're a better engineer if you don't need the formula. You can always just go back to first principles because it's something that happens. In certain fields of engineering, often, if it doesn't happen in your field, it probably doesn't matter. Okay? So anyhow, so we have this, right? So that's basically, well, what is that? Your delta R is approximately equal to R prime of T delta T, right? What's that? That's this. And delta S is the magnitude of delta R. And from what you've done with three-dimensional figures and stuff, you understand that that magnitude is just going to be dx dt squared plus dy dt squared plus dz dt squared, right? And of course, square root of that Pythagorean theorem. So this is what you integrate. Well, that's a formula we just saw in there. You probably didn't pick up on it, but I saw it and said, yeah, I probably ought to explain this. So, delta S is the integral from t equals a to t equals b. Of this, right? With respect to t. There's your arc length for any parametric curve. Now, for many curves, you can't do the integral. You have to approximate it, but, and of course, this would be the integral from a to b. We don't really have to write t equals a to t equals b since we're specifying dt out here, right? Just wanted to emphasize it here. So I'm just going to write integral from a to b of the square root of x prime squared plus y prime squared plus z prime squared Okay? Okay, well, I'll try to give you a reasonable assignment in the parametric equations at the level I think you can work. Okay? And if I underestimate or overestimate the level, I can give you a longer assignment. I'll try to keep it relatively brief because I think you understand things pretty well. I think you'll be able to make the jumps. But remember, there are always other problems that I haven't assigned that you can use to help prepare yourself to do the ones that I have, right? But based on the work you've done and my familiarity with your work, I think I can give you a relatively modest number of problems of relatively moderate challenge as opposed to a bunch of easy problems, busy work. Okay? You can always do the busy work problems if you need to because you can do those quickly. Fair enough?